Okay, let's do another one. An ideal gas initially at 20 degrees Celsius and 200 kilopar, you can see the pressure is now given in Pascal, has a volume of 4 liters. It undergoes a quasi-static isothermal expansion until its pressure is reduced to 100 kilopar. Now, what is a quasi-static change? A quasi-static change is a change, you see, isothermal, so that at every state of the change, the temperature remains a constant. In other words, the change happens in such a way that equilibrium conditions are established very quickly. That is a quasi-static state. So an ideal gas initially at 20 degrees Celsius and 200 kilopar has a volume 4 liters. It undergoes an isothermal expansion. That means the temperature remains a constant until its pressure is reduced to 100 kilopar. Find the work done by the gas and the heat added to the gas during the expansion. Now, before we go to the problem, let me ask you, do you remember the equation we developed for work done in an isothermal process? W isothermal, what is that equal to? Right? It is nRT ln V2 over V1. We might need that for this problem. Alright, let's pick the data. T1 is 293 Kelvin. P1 is 200 kilopar, which is 200,000 par. V1 is 4 liters. P2 is 100 kilopar. And we need to find the work done by the gas. Now, you can see how useful our ideal gas equation is. We got PV equal to nRT. So, if you look at the stage 1, we got T1, we got P1, we've got V1. Therefore, we can now find the number of moles of that gas. Why do we need the number of moles? Well, the equation for the work done contains nRT ln V2 over V1. We need the number of moles of the gas. So, you are given the value in state 1, you know the temperature, you know the pressure, you know the volume, therefore you can calculate N as PV over RT. P is 2 kilopar, that is 2 times 10 to the 5 Pascal. V1 is 4 liters, 4 times 10 to the negative 3 meter cube. Always keep the units in the right form. Divided by R is 8.314. Remember, when you use pressure in Pascal and volume in meter cube, the value of R is 8.314 joules per mole per Kelvin. And the temperature is 293 Kelvin. Very, very important to convert that Celsius to Kelvin there. And that gives me, you got 0.328 moles of gas. Okay, now if you look at the equation again, what is it that we are missing here? Work done in an isothermal process is nRT. We've got N, we've got R, we've got T, ln V2 over V1. We've got V1, we don't have V2. So what do we do now? For an isothermal process, what is the equation for an isothermal process? I'm going to cover that with my head. What is the equation for an isothermal process? PV is a constant. What does that mean? It means P1 V1 equal to P2 V2. Well, we know P1, we know V1, we know P2, therefore we can find the V2. So V2 is P1 V1 divided by P2. And now P1 is 200 kilopower, V1 is 4 liters, P2 is 100 kilopower. I haven't changed anything there because I left the pressure units in kilopower, numerator and denominator. I left V1 in liters so that I will get V2 also in liters. So this will be 8 liter. I hope you understand why I did not write any units there. This is 200 kilopower times 4 liters divided by 100 kilopower. So that gives me V2 equal to 8 liters. And now, if you go back to the equation for the work done in isothermal process, nRT ln V2 over V1. We've got the temperature, we've got N, the number of moles, we have V2, we have V1. We can now use the equation to calculate the work done. W isothermal is nRT ln V2 over V1. That will be, the number of moles is 0.328, R is 8.314, T, the temperature is 293, times ln V2 over V1. You can see, again, I left them in liters. Does it make any difference? No, because it's a simple ratio. So I can leave it in any units as long as both are of the same unit. And that gives me the work done is 554 joules. That is the work done in that isothermal process. And we now need to find the heat added to the gas during this expansion. And what we now know is that the work done is 554 joules. dQ equal to dW plus du. And for an isothermal process, what is du? I should have asked you that. What is the change in internal energy for an isothermal process? An isothermal process is the temperature remains a constant. And internal energy is given by 3 over 2 nRT, where T is the change in temperature. Since there is no change in temperature, there is no internal energy change. Did you understand that? We said earlier that internal energy of a certain amount of gas at a very low density depends only on the kinetic energy. In other words, depends only on the temperature. If the temperature remains a constant, there will be no change in the internal energy. So what is the change in internal energy for an isothermal process? du equal to 0. So dQ equal to dW plus du, that reduces to dQ equal to dW, and we know dW, therefore the amount of heat added during that process will be 554 joules. I hope you now understand the method of solving these kind of problems in thermodynamics. Alright, I think that will be enough for this lesson, and I will get back to you for the next lesson a little later.